Operations in modern warfare require commanders to make rapid, high-stakes decisions based on fragmented intelligence, enemy movements, and logistics. The sheer volume of this unstructured data routinely outpaces human cognition. Military theorists have long called this the fog of war. It is the historical burden of operating with incomplete, confusing, and rapidly changing information. This slide shows a real attempt to map that complexity for military commanders in Afghanistan. A single operational decision requires a commander to simultaneously synthesize troop capacities, economic infrastructure, tribal governance, and popular support. Each node interacts with the others. This diagram shows how militaries historically manage this, building rigid models that sorted variables into hierarchical boxes to predict outcomes. But human conflict isn't mathematical. Social and political variables are messy. A static campaign model breaks down when it meets reality on the ground. Human cognition cannot keep pace with the exponential growth of modern battlefield data. That structural limitation forces militaries to seek a technological intervention. That intervention has arrived in the form of AI decision support systems. An AI DSS is a software platform that uses artificial intelligence to synthesize battlefield data and generate tactical recommendations for human commanders. The doctrinal goal here is cognitive augmentation. Militaries are generally not deploying these systems to create autonomous warfighting machines. They are deploying them to help humans think faster. The software ingests unstructured data streams from drones, satellites, and communications, filtering the noise into a prioritized list of actionable targets. The algorithm handles the data sorting. The commander simply reviews the system's selected pathway and authorizes the strike. This use of AI to optimize course of action generation is called decision intelligence. Integrating deep learning models into the targeting cycle solves the speed problem, but it introduces severe, systemic vulnerabilities across three specific vectors. Deploying algorithmic speed without deeply understanding the architectural fragilities of these models amplifies operational risk. The first vulnerability vector is scope. In machine learning, algorithms frequently suffer from distribution shifts. A distribution shift occurs when the real-world data an algorithm encounters during deployment differs meaningfully from the data it was originally trained on. Deep learning models are mathematically brittle. They optimize for the specific patterns in their training environments, and they fail when forced to operate outside those exact parameters. This overhead image shows a computer vision model trained to identify flooded buildings in the Houston suburbs. The algorithm achieves high accuracy here because the building spacing, rooftops, and infrastructure follow a uniform grid-like pattern that matches its baseline assumptions. This second image tests the exact same algorithmic parameters in a radically different landscape, the flooded region of Orenburg, Russia. The dense, irregular layout, varied building sizes, and different infrastructure patterns cause the algorithm's accuracy to collapse. It cannot interpret shapes it has never seen. Translating this to military doctrine, if a commander takes a tactical AI DSS trained for a specific counterinsurgency environment and applies it to a strategic problem in a new theater of war, the model's math breaks. Flexible software creates a false sense of capability. When commanders confidently deploy algorithms outside their validated parameters, the system outputs catastrophic errors. The second vulnerability vector is data. We must draw a strict distinction between modeling systems governed by physical laws and systems attempting to model human behavior. Physics-based data allows for highly accurate, near-term predictions because the mechanics, like velocity, arc, and gravity, are fixed. Human-based data, such as social uprisings or enemy strategy, is only observable indirectly. Human choices do not follow physical laws. This creates what is known as irreducible uncertainty. Irreducible uncertainty is a baseline level of unpredictability in a system that cannot be eliminated, no matter how much additional data you gather. If you flip a fair coin 100 times, the data will prove a 50% probability of landing on heads. That data provides absolutely zero certainty on the outcome of the 101st flip. Because of irreducible uncertainty, no AI system can definitively answer the question, what will the enemy do next? The military also faces a scarce data problem. Adversaries actively hide high-value capabilities, which results in sample sizes that are simply too small for robust machine learning pattern recognition. AI predictions derived from scarce, non-physical data create an illusion of mathematical precision. They mask the reality that human judgment is still strictly required to interpret the battlefield. The final vulnerability vector is human-machine integration. This introduces a psychological phenomenon known as automation bias. Automation bias is the tendency of human operators to trust automated recommendations, even if their own senses indicate the machine is wrong. Under high-stress, time-compressed combat conditions, humans actively look for ways to reduce their cognitive load. They default to trusting the machine. This becomes highly dangerous when militaries utilize large language models as natural language interfaces. Large language models, or LLMs, are deep learning algorithms trained on massive datasets to recognize, summarize, and generate human-like text. LLMs natively hallucinate. They fabricate rationales that are designed to align with user expectations rather than reflect objective truth. This creates a dangerous feedback loop. The system outputs a confident falsehood, and the operator's automation bias drives them to accept the erroneous recommendation. The human in the loop is designed to act as a protective failsafe. Instead, flawed human psychology makes the operator a conduit for algorithmic errors to enter the physical battlefield. We saw the real-world application of these vulnerabilities during the 2026 Iran war scenario. That conflict was defined by the sheer speed of AI-driven target generation. AI platforms dramatically accelerated the military kill chain. Forces processed 1,000 targets in the first 24 hours of the conflict and 5,000 targets over 10 days. This reveals a speed and accuracy paradox. As the AI drastically compresses the time required to act, it scales organizational bias and removes necessary friction. Operating at this tempo without guardrails led to severe consequences, including the airstrike on a civilian school, where AI targeting involvement was heavily suspected, resulting in 170 deaths. Unchecked algorithmic speed strips away the necessary time for critical human evaluation. It effectively turns software hallucinations into mass kinetic casualties. Mitigating AI risk in warfare cannot be solved purely by software engineering. It requires doctrinal governance. Commanders must establish specific, reversible, and context-based criteria dictating exactly when and where an AI DSS is allowed to be deployed. Second, militaries must mandate continuous certification cycles. This continuous feedback loop is required to actively catch the distribution shifts that inevitably occur as the battlefield environment evolves. Units need responsible AI officers. AI tools require the exact same dedicated safety oversight as kinetic weapon systems or aviation units. True cognitive superiority on the modern battlefield is not achieved by trusting the machine's autonomy. It is achieved by rigidly and actively architecting its boundaries.